Well, guys, I'm back. We're going to now do a video on answering the question that I asked. I had two responses mainly on it. Both good responses. And quite correct to a degree. And we'll go into that. Because we're going to take it to another level a little bit. Try to keep it simple, but we're going to take it to another level. First, let's analyze something. First of all, to answer the question, I asked the question, does current flow through a wire? Does it flow on the surface of the wire? Or both? Well, the answer is C, both. And despite a certain book that we looked into from 1955, no matter what frequency, it's both. Now there are certain things and factors that happen here, and we'll get into that. But first, let's just see what's going on. We have, and that blasted thing, I think I just lost my black, so we're going to go, I'm fond of purple, so we'll go purple. We have this nice little wire here. Now I'm not going to draw it in 3-dimension or circle or anything that matters or not. When there's nothing going on, in other words, we're not hooked up to a current flow, to a battery and a load, then we have some free electrons. All conductors have free electrons. There are electrons in a shell. It used to be called an orbit. It's more of a shell. That's the outside of the atom, the outer edge. To go in depth a little bit, take you back to high school physics. An atom is made up of a nucleus which will have one or more protons. It may also have neutrons in there, but we won't care about those. If the atom is neutral, then whatever number of protons it has in the nucleus, it has electrons that are going around. The Bohr model was basically in an orbit, kind of like the planetary system. We know now that it's more like a cloud, and these clouds are located in certain shells, so we call them shells now instead of orbits, but whatever. Anyway, due to a certain phenomenon called quantum physics, the first shell you can have like 2 electrons, and then the next one 6, and so on. Okay. If you got a piece of wire, say copper or something like that, you have an atom. It has a few shells, but the outer shell is also known as the valence shell, and the electrons that's there is known as the valence electrons. Those guys are the furthest from the protons, so they have quite a bit of energy, and they can actually break free and kind of roam around. They'll go from one atom to another and back, and just kind of go whatever directions they want to. That's what makes a conductor is those valence electrons that are free to kind of move around. Well, what actually is going on is they just kind of do a random pattern. You'll have one go this way, and and then he might bounce off and go this way, and then bounce off and go this way, and bounce this way, and this way, here, and just all different weird directions. That's with nothing hooked up. And this is going on throughout the wire. When I hook up a source to this, right now we'll look at DC and then we'll move into AC. So I hook up a source. What actually happens is we have our magnetic field, like I talked before, all of a sudden develops. It senses this magnetic field. And what it starts doing is it starts trying to push these random motion electrons in a direction. Okay? Well, they kind of drift in that direction. It becomes more like, oh, let's use a different color just to kind of enhance it. It becomes more like, you know, they might have been going this way, and, you know, but then they'll kind of bend, and then maybe it'll bounce off here and go a little bit like that, and then bend over to here. And you may have another guy that wants to go this way, but just kind of has to bend this way. So they're getting bent and drifted along in that direction. So that's what's happening. Now AC is no different, except now it kind of drifts them this way, then it kind of drifts them this way in the next fraction of a second. And this is where we're going to start getting into some interesting things. At low frequencies, including RF low frequencies, there was, and I don't remember, and I tried looking it up, and a lot of my sources are getting very old and difficult to find, and my memory's terrible on it. But there was a paper wrote sometime, I want to say the early 70s, like 72, 73. It might have been a little later than that. That redefined high frequency and redefined what was going on. Partially because we were starting to move into areas of much higher frequencies. In that time period, we started looking at gigahertz for the first time ever. And we had to redefine it because things started changing. What is wrote and what one person quoted out of a book, Electronic Radio Engineering of 1955, is correct to a point. It has been found that as you move up in frequency, things start changing again a little bit, and mainly because of other factors. And these factors have to do with, well, it has to do with quantum mechanics, the quantum nature of electrons, and it also has to do with theory of relativity. Now, relativistic collisions and relativistic motions inside the wire. These create other dilemmas and stuff, but they also do some funnies. Alright, first let's look at the surface of the wire at high frequency. Now we're not going to pick a frequency yet, but it has been determined in a general sense. A certain frequency, and you go above that frequency, things start changing. Below that frequency, things stay more closer to looking kind of like a DC circuit. And in DC, there is movement on the surface as well as inside the wire. Just that there's not as many free, easy, attainable electrons there. They kind of are moving inward like this, but so the drift seems to be more inside the wire as opposed to the surface, but it still has current on the surface and interior. And it's actually pretty equal technically. with AC, things start changing a little bit. But let's look at the surface at high frequency. At high frequency on the surface, see on the surface, unlike having a lot of this randomness, on the surface the electrons want to go in, so they're wanting to go in. They like to just bounce in here because they're trying to head towards some positive charge somewhere. But they're also going to be reflected out a little bit because of the fact that there's a lot of negative charge. So the negative charges are repelling them, but the positive charges are pulling them in. And if I get, if I get a few electrons that have deflected out this way inside the wire, then that makes that look a little more positive, and this guy out on the outside wants to go in. But when you start putting a current to it, they kind of line up a little better. They will line up easier on the surface and drift a little better on the surface of the wire as opposed to the interior of the wire, because there's a huge number of collisions. They can actually move a little faster on the surface than they do because they don't experience near the collisions. But when you got AC, at one point you're wanting to go this direction. Another point in time you're wanting to go this direction. So you got these electrons, one point they want to go this way, and then all of a sudden another point they want to go this way, and back and forth. Well, this brings up a problem as the frequency goes up. It develops a resistance that has nothing to even do with magnetism or inductance or anything. It has to do with momentum. And you will see it inside, but it's not as prevalent inside the wire. Now, let's erase this for right now. To give you some idea what's going on here, let's say you got a shaft, and on that shaft I've got this giant flywheel, and it's got this nice little handle here for you to grab a hold of, and this shaft is is hooked and mounted on this base, and the bearings in here, let's say, are ideal, no friction whatsoever. So if you gently push on that flywheel on the handle, it'll move without too much trouble. Let's say the flywheel is like, it's massive, I don't know, say a 100-pound flywheel. Now, in a DC circuit, we only flow in one direction. So a DC circuit is like you going up to this flywheel and you just start it rotating. Now, initially, it takes a little bit of energy to get it going, depending on how fast you want to try to get it going and how quickly you want to get to that point. But once you get it going, it don't take much at all to keep it going, because momentum wants to stay going. The deal about momentum is that once something is moving, it wants to stay moving. So this flywheel has no problem staying rotating. It don't take much to keep it going. And in fact, if it was in a perfect vacuum, perfect bearings, everything was perfect, once you got it going, you just walk away and leave it, and it never stopped. Now let's look at an AC circuit. Low frequency AC, not so big of a deal. And low frequency AC would be, you got it rotating in one direction, and then all of a sudden you realize you're going to have to go in the other direction, but you got some time. It's low frequency. So you can gently start slowing it down until you get to a stop, and then start speeding it up in the opposite direction. Not a problem. But what happens at high frequency? Well, high frequency, you have to do this a lot faster, almost instantaneously. So it's like you get this thing rotating, say 30 RPMs, and someone tells you right now it has to go the opposite direction at 30 RPMs. This instant. Not a second from now, not 10 seconds from now, not a minute from now, but right now. It's not impossible to do that, although I don't think any human could. A machine could, but it's going to take a lot of force to do it. And the reason is because anytime you change direction or you change speed, that's acceleration. Force equals mass times acceleration. The mass is not changing. So what's changing, because we want to change its speed and direction at the same time, is our acceleration. Well, acceleration is a measure of change in a period of time, how long it takes. And the faster that I want that acceleration, the faster I want to make that change, the greater the acceleration, thus the greater the force. Well, what does that do with electrons? I got these little electrons inside this, on the surface or inside the wire. And right now, I'm saying go this way, or at least drift in that general direction. Now at low frequency, it's no big deal. They get going and I tell them, now go the other way. Well, that's not so bad. It don't take that much force to do that. But what if I tell them, okay, go this way, then this real fast? They're going to resist. It's going to take a lot more force to do that. Even though that mass is extremely small, now we're asking them to do and change its direction extremely fast. The acceleration is real high, so it matters not that the mass is not great, the force is still quite a bit. That resistance, and it is a resistance that shows up in the circuit, in the wire, and it's a resistance to the current flow. So higher the frequency, you'll see that. Now that's primarily on the surface because of the randomness and the number of electrons and the bending angles and everything else. Inside the wire it's a little easier, so it takes less force. So the surface builds up resistance. Inside, not as much. But inside, we do have inductance that builds up. We have actually little magnetic eddies that build up. But as frequency goes up, those eddies get weird. Because of the drift and because of the random directions that's happening in here, and of course sometimes when they may be going this way and then this way and everything, because all this weird randomness that's going on, and the faster that's happening and changing and everything, the eddy currents start getting really strange. The little eddy magnets, you know, they'll start going like maybe this way, and some will go like this way, and some will go like this way, and like this way. They start getting all kinds of weird angles to them. And sometimes they help out with the current flow, sometimes they fight against the current flow, sometimes they don't affect it whatsoever. This is when you're getting into the ultra high frequencies. This is what happens when we get way on up there into several hundreds of megahertz and on into the gigahertz and up in the upper echelons. This starts happening, and this is caused by quantum effects and relativistic changes, because we're trying to make those electrons, the drift itself even change direction approaching the speed of light. Things change then. Everything starts changing. Quantum mechanics start coming in effect, and you start getting a very unusual and difficult to understand flow of current. In cases like this, the current tends to want to go to the outside, because out here we don't have near as much of that, but out here we have the other problem with the resistance. So it starts becoming a battleground of which is greater. Current likes going down the path of least resistance, but it starts becoming a battleground, and certain frequencies tend to allow more current to flow through and less on the surface, and other frequencies, and some of them can be very close to each other, the opposite's true. So in design, when you're working with those kind of frequencies, you have to decide, when you're looking at a particular frequency, some of these are known, some aren't yet, but that will make a determination of what you're using for conductors, maybe even materials for conductors. Their shapes and everything will be determined more by the frequency in those real high frequencies, those ultra high frequencies, because some frequencies things work better interior as opposed to surface, others it's just the opposite. So anyway, as far as our purposes go, and most of you are concerned about, with radio and old TV, say in the, that deals with VHF, and mainly you're looking at like channel 3, but even any one of the VHF channels, for the most part, the current really is flowing and making complete usage of the entire wire through and on the surface, and that's good enough. Now, yes, granted, getting in the upper echelons of the VHF, it will be a little easier on the surface for it than interior because of magnetic reasons and inductance, but it's not drastic. It's not like super amount. So to answer the question, really, as long as I've got kinetic energy, in other words, as long as I've got an operating circuit, current is flowing both on the surface and through the wire. In actuality, on all frequencies, just some frequencies and high frequencies, things start getting really weird. Sometimes it works at certain levels. It works so that it's mostly on the surface, but there's still current flow inside. But as you go on up, things start getting strange and stranger. And then we start getting really weird things. And when you get really high, things get really weird. And we start developing conductors and everything that are more like waveguides, that we call waveguides, as opposed to actual conductors, because it's the only way to get the current to flow. It starts bouncing around and stuff, and that has to do with the quantum nature and the relativistic changes due to the speed of the frequency. So I hope that you kind of understood it. I hope I didn't lose anybody on this. It suffices to say that and I call low frequency, and what I call low frequency is pretty much anything on radio. And let's just say anything below the FM and below. Let's pick a number like 110 or 130, maybe even 200 megahertz and below is low frequency, and current's going through and on the surface of the wire, and that's the easiest way. Now the times when this doesn't happen is when you have static electricity. In static situation, the charge builds up on the surface and neutralizes interior, so all the charge is on the surface of whatever you're building static on. But that's only in static. As far as conductors go and electricity, then you get the flow making use of the entire wire. And for, like I said, for our usages, just consider it going answer C, that it goes through and on the surface of the wire relatively equally. So anyway, I hope that answers that question. Gosh, this got long. I didn't even think I was talking that much. And I'm just trying to think. That'll probably do it for my videos for today. It'll probably be a little while, at least a week, before I make another video. So enjoy these, and I'll see you in probably hopefully a week and stuff, and we'll get back to the transformers and some other stuff. I'll find something else to work on or interest. Maybe even do some radio work or something like that. So until next time, thanks for watching, and if you have any questions, just post them, and if it's something I can quickly answer in a sentence or two, then I will. Otherwise, I'll make a video. Thank you.